Let's do 1.6. The heat flux through a wood slab that's 50 millimeters thick, whose inner and outer surface temperatures are 40 and 20 degrees Celsius respectively, has been determined to be 40 watts per meter squared. What is the thermal conductivity of the wood? Okay, so we're given a wood slab. We have a length 50 millimeters, 0.05 meters. The inner temperature I'll call T1. It's 40 degrees, outer 20, and then the heat flux is 40 watts per meter squared. And they want us to find the thermal conductivity. So that's K. What did I just do? All right. So if we draw our schematic, so we have our wall. We have T1 here, say T2 down here. This is the X direction, from left to right. That distance, thickness is L, all right? Then our heat flux is through this wall, right? So if we're looking at this, there's a few assumptions that go with this. We have 1D, right? We only said we have X direction, right? If there's heat, we don't have heat going up in the Y direction, you know, vertical or Z direction, outer into your paper or computer. Then the other one, steady state. And then the next is constant properties, so that our thermal conductivity is not changing with distance, right? That it's, if it's a property like thermal conductivity K, it's not changing at the left wall versus the right wall, like it's not a function of that distance. Okay. All right, so where do we begin? How do we solve this problem?
We just use the flux equation for conduction, right?
Mm-hmm.
So that's Q double prime is equal to K times T1 minus T2 over the length.
Yep, so that's raised law. All right, so the basic one is this, right? So that's the Fourier's law, x direction. That's saying positive heat flux would be from left to right, because that's our positive x direction, okay? Even with that negative sign, right? So if we utilize this, right, we can also simplify this to negative k T2 minus T1 over L is our dx, and then that's what you heard classmate say was the k T1 minus T2 over L, which is switching these to get rid of that negative. All right, we're looking for K, so K then has this, right? We were given heat flux, length T1, T2. So then we solve, we get 0.1 watts per meter Kelvin. Okay. Any questions on that? Pretty straightforward. But I wanted to show you another thing that, a way of looking at this equation is you have, we said it would look like this, K T1 minus T2 over L, right? Well, there's a parallel to electrical circuits in this case. So if we think of heat flux as current, then we have a change in voltage over resistance, right? So if we think of that, then we have heat flux is our current, right? We have a change in temperature is like our voltage, and then we'd have an R conduction, which is then just L over K, our resistance from conduction. Okay, so a very small resistance will keep the temperature, the same, T1 minus T2. Or a very large resistance, like insulation, will have the wall temperatures being very far off from each other. Okay? From one side of the wall to the other. Okay? Questions on that? So we'll use this kind of parallel a lot to the electric circuits. All right, so let's do 1.15. The free convection heat transfer coefficient on a thin, hot vertical plate suspended in still air can be determined from observations of the change in plate temperature with time as it cools. Assuming the plate is isothermal and radiation exchange with its surroundings is negligible, evaluate the convection coefficient at the instant of time when the plate temperature is 245 degrees Celsius and the change in plate temperature with time, dt is negative 0.028 Kelvin per second. The ambient air temperature is 25 degrees Celsius, and the plate measures 0.4 times 0.4 meters with a mass of 4.25 kilograms and a specific heat of 2,770 joules per kilogram Kelvin. All right, so we're given an isothermal plate they tell us to neglect radiation. And then we have the surface of the plate is 245 degrees Celsius. Change in temperature with time is 0.028 Kelvin per second, so negative. And then the air temperature, surrounding air, is 25 degrees Celsius. The plate, area of the plate, is 0.4 meters by 0.4 meters, which is 0.16 meters squared. The mass of the plate is 4.25 kilograms. Specific heat, 2770 joules per kilogram Kelvin. They want us to find the convection coefficient. That's H. All right. All right, so our schematic basically looks like we have this plate. And some wires are supporting it. Okay. Okay. So we have this process going on, right? The other thing you can think about is if we think about this on a temperature versus time plot, we might have something like this, where the temperature of that plate, it's dropping. You're putting in a hot plate in surrounding air that's 25, so it's cooling down, right? And they gave us one instant, so it's 1 point on this plot. So that would be, let's say it's right here. So it's at that time, and at that temperature of the surface. So that's what we're given right here. Okay. And then this dt is the slope at that point, right? So that's dt. So we could do this at a whole bunch of different points and how it changes with time, right? But they give us kind of one instant right here. We have assumptions. They gave us a couple in the problem, which I gave as givens, but isothermal plate, neglect radiation, and then the other is, there's kind of two of them, but I'll leave the first one. No heat transfer through the wires. Okay. All right, so then if we're analyzing this problem, where do we start?
Conservation of energy.
All right, so our COE, okay. All right, so we have this. Now what?
I don't think, is there anything being generated? I mean, there are wires connected to it, but I don't think there's anything that's saying that there's no heat transfer to the wires, so E dot G goes to 0.
Yeah, so there's no, yeah, they're just hanging, they're suspending it, so there's no power going through the wires. Yeah.
Oh, okay.
Yep. Okay, anything else?
There's no energy in, right? Because it's cooling down over time.
Yeah, so if we kind of made a zoom in of the schematic, so I would even do this first before what you guys are, simplifying it, is there's no energy in, but a good way is what heat transfer is occurring on this plate. Let's label it, right? We have our plate right here.
The exothermal.
So what?
Like it'd be heat going out, right?
Yeah, but what type of heat transfer going out?
Convection out.
Yep. Okay, so we have convection. They told us to neglect radiation, so that was an easy one. We said there's no energy generated since we're not putting any electricity into it. Okay. Is there conduction?
No.
No. So conduction would be inside the plate, right? If there was, but it's also isothermal. So that's telling us that, dt dx that's in our Fourier's law is 0, right? Because there's no temperature change across it, so there's no conduction inside of it. But regardless, even with that, we're doing our boundary around the whole thing. Okay, so that then means we're just looking what's coming and going outside of it. Okay, and so we just have convection. We said, look at that, and like we said, there was no energy in because of, we said we're not putting any energy in, and also our schematic. If we label our schematic, it tells us there's no energy in. We just have change in energy with respect to time and our energy out. Okay. This should be negative right here, huh? Okay. All right, so then again, it's a plate, so it's a solid, it's incompressible. So we can simplify the mass and the specific heat aren't changing, and we can simplify it and pull those out and have mc dt dt. Okay.
So, Professor, we can make that connection from d e storage dt to mc dt dt if we're neglecting KEPE and we're saying it's incompressible, right? Or is there anything else?
No, that's it.
Okay.
Yeah. All right, so we have then, they gave us mass, specific heat, dt dt, convection, right? What equation is that?
Convection flux times area, which will be H times T infinity minus TS, or TS minus infinity times area.
Yeah, so that's Newton's law of cooling, right? So is it TS minus T infinity, or?
It's TS minus T infinity, but once you throw in the negative, it'll be T infinity minus TS.
Okay. So a good way of remembering which one it is as long as you stay consistent from your schematic to what you write down, as long as that's consistent, even if you guess the wrong direction, the problem will fix itself. Okay, so here we have out, which means we follow the direction of our arrow. Okay, so that means we have TS here, T minus T infinity there when we write it down. Okay, so that has H area TS minus T infinity. So even if we thought this was energy in, let's say we labeled this, instead we said, oh, no, this is, when we were, we guessed it was a problem that wasn't straightforward, it's convection in. Well, then it would have been positive HA, but it would have been T infinity minus TS. Well, oh, we guessed wrong. So TS is greater than T infinity. Well, guess what? This is going to figure itself out. And, this one, now this will be greater than this. Okay. And you'll have heat out still. Okay. Because TS will be greater than T infinity. So as long as you're consistent between your arrow on your schematic, right, which is this, with your, what's subtracting what here. Okay, if you mix those up, then you'll get it wrong. But if you guessed heat in, then it's T infinity minus TS. If you have T it out as convection, then it's TS minus T infinity. Okay. All right, do I have anything incorrect in this equation?
No.
It sounded like a question mark.
Yeah, I don't think there's anything wrong with it.
All right, so let's go through it. We have this given to us, C mass, T infinity, TS, convection. So what's this area?
We were already given it, right? The 0.16 meters square.
Okay, so they gave us 0.4 times 0.4, right? So they gave us this area. Is that where convection's occurring on?
No.
Would it be double that?
Yeah, so we would double that, and there's also kind of an assumption on there. It's a thin plate, right? Because if we really wanted to be super accurate, right, we would include the sides of the plate too, right? But if it's a thin plate, those sides, that area is not much compared to the, like, this area here and here is not much compared to the orange, right? So then we have to double it. Okay, so that's a, any place the fluid is touching, right? The air surrounding it is touching. That's the area that the convection is occurring on. All right. So now we can solve for, they didn't give us convection. That's what we're solving for, sorry. Convection coefficient in this problem, which is 4.7 watts per meter squared Kelvin. Any questions on that? Okay. Couple comments from me. So in this first assumption that they gave us, this isothermal plate assumption, we'll actually look at this in chapter 5 in depth, like have a way to tell whether we can make that assumption. Okay. In chapter 5, because it has to have high thermal conductivity to, compared to conduction, or sorry, high thermal conductivity or conduction compared to convection to make that assumption. Okay, but it told us to make the assumption in this problem. But we'll look at that in more depth when we can make that assumption and when we can't, which allows us to do a simpler analysis. The next one is
So I have a question real quick.
Go ahead.
So I'm kind of seeing a trend with the coefficients of conduction and convection. So what exactly is the equivalent of H for radiation, and does it have units of watts per meter cubed Kelvin?
What's the equivalent? For radiation, I mean, there is a way to, we have, oh no, here it is. When we were defining radiation, here, yeah. So radiation, looks like this, but we can linearize this to make it kind of look like convection. So then we can have an equation like this where now the radiation convection coefficient looks like that, and that would have that same units.
Okay.
But most of the time we don't use this version, and we use the version here, okay. Which has t to the fourth, because radiation has that fourth power. Because even here you have all this whole thing that's kind of creating that. So it'll have that same radiation throws a wrench in analysis just because of that, because that temperature of the fourth makes things a little more difficult to solve when you have everything going on at the same time. So it's not as simple to isolate temperature by itself when you have something to the fourth power, right?
Okay. All right. Thank you.
Yeah. So in this one, they also told us to neglect radiation, but we could have checked whether that is an appropriate assumption. So in that, just by using those equations I just shown, right, we could have used this equation right here, okay, and just found the emissivity of the plate, right? So what type of plate material is, look it up, and saw whether this, and solve for the radiation heat flux, and compared it to our convection heat flux that we had here. Right here, right, and compared it, and if the convection was much higher than the radiation, then us neglecting radiation is a good assumption. But if it's in the ballpark of the same quantity, right, it's around the same in value, now they both really need to be included in that problem, right? Or if, let's say, radiation was dominating, then maybe you can neglect convection. You can neglect convection and just include radiation. So you got to compare the convection versus radiation. Do they both stay in, or can you get rid of one or the other, okay, if you're neglecting it? So that's a way to kind of compare whether you should be neglecting something or not, like radiation. All right. All right, so let's do (1.23). Under conditions for which the same room temperature is maintained by the heating or cooling system, it is not uncommon for a person to feel chilled in the winter but comfortable in the summer. Provide a plausible explanation for this situation with supporting calculations by considering a room whose air temperatures maintain at 20 degrees Celsius throughout the year, while the walls of the room are nominally at 27 degrees Celsius and 14 degrees Celsius in the summer and winter, respectively. The exposed surface of a person in the room may be assumed to be at a temperature of 32 degrees Celsius throughout the year and to have an emissivity of 0.9. The coefficient associated with heat transfer by natural convection between the person and the room air is approximately 2 watts per meter squared Kelvin. What is the ratio of thermal resistance due to convection to the thermal resistance due to radiation in the summer? What is the ratio of thermal resistances in the winter? All right, so we really won't do this stuff with thermal resistances, but we'll talk about the other part. So we have then person, right, in a room. So person in a room, the air surrounding the person, so that's T infinity, is 20 degrees Celsius, okay? The surroundings, so the walls during the summer, 27 degrees Celsius, which is 300 Kelvin. Surroundings are the walls during the winter, are 14 degrees Celsius, or 287 Kelvin. And then the person has a surface temperature of 32 degrees Celsius, which is 305 Kelvin, and an emissivity 0.9 was given, and then there's a convection coefficient of 2 watts per meter squared Kelvin. Okay. They want us to find why does this person feel uncomfortable in the winter? Basically, they have the thermostat set for 20 degrees Celsius, or that's 77 degrees Fahrenheit. All right, so our schematic. We have our person. They're feeling a little uncomfortable, right? We have the walls. Okay, so that's the surrounding walls. And they have the summer, and you have surrounding walls that are different temperature in the winter. The air in the room is at T infinity and convection coefficient. Okay. All right. So where do we begin? What heat transfer is occurring off of this person?
Radiation.
We have radiation. Anything else?
And convection, and convection.
Yeah. And we have convection. Okay. And if we make a boundary of the person. So there's no conduction off of the person, right? So the conduction, if we were trying to look at conduction, it would be inside the person, right? So that would be more of like, say, their core temperature to their surface temperature of the skin or something like that. That would be conduction. That'd be inside that person. All right. So then the total heat leaving the person, we just sum those up. All right, so if we do Newton's law of cooling again, for convection, We have the surface temperature of the person, T infinity. We have our convection coefficient. Those are all given. So we get 24 watts per meter squared. Okay. Does this convection heat flux change in the summer or winter?
No.
No. Okay, the surrounding air's temperature or your thermostat still set to 20 degrees Celsius, so that's the same. Okay. Radiation now. We have a summer, and we're going to use back to our equation right here, which is our small surface in large surroundings. And we have winter. All right, so if we look at this, do we have all the values for these equations?
Yes.
Yeah. Okay, so they gave us emissivity, Boltzmann's constant is just a constant, and we have surface temperature of the person is the same in the summer and the winter, but the walls temperatures are different, okay? So we get then 28.3 watts per meter squared in the summer, and we get 95.4 watts per meter squared in the winter. Okay, so in the summer, you're feeling this heat transfer, right? And then the total of those two together would be your heat flux. And then in the winter, you're feeling these two, okay? So that radiation heat transfer is much higher. Okay, so you feel colder, okay? So a person feels heat flux. It doesn't feel temperature, okay? So that's the difference. You know, when people get mixed up of temperature versus heat transfer, that's one of the big ones. Okay, because you're thinking, you know, room temperature is why you're feeling something. It's you actually feel heat flux. You do not feel temperature. Temperature can be the driving force for the heat flux, but it's not what you feel. Any questions on that?
So if we were to put this into the conservation of energy, then it would have an overall negative value, right?
Yeah, you would just have energy out, but you're generating, you know, if you're thinking about yourself as a person, you know, if it's steady state, you know, you would have a generation.
Right.
You're generating energy inside your body. So that's where, if it's steady state, where, you know, where it all equals out.
Right. But like in an actual situation, we would still have some sort of energy storage, right? In a room.
In the room, or so our boundary is the person, right?
Right.
So we're keeping
Okay.
our same body temperature. So we would have an energy. So if it's that your body's at steady state, you know, you're not just,
Okay.
you know, if you're in that room and you're at steady state, like you're just not gonna, you're gonna have generated equal to the energy out that's leaving here. Okay, so
Okay.
that's how, you know, you have to, that tells you your calories. You're consuming this much to keep your body temperature this, or you have to consume because of the energy generated that you have to generate to deal with that heat transfer that's leaving your body. Right?
Okay.
Yep. Any other questions? We can also do this experiment of, you know, that you feel heat flux and not temperature is with, say, let's say you have a block of steel, right? And then you have a block of copper, right? And they're at the same temperature. And now you put one finger on this block of steel, and you put a finger on the other hand on this block of copper, okay? Well, there's conduction now, because you're putting your finger against a solid block. It's not just fluid where you had here, right, surrounding this person. And there's conduction here, right? The copper will feel cooler. It'll feel colder to you. You will think the copper is at a lower temperature because you're feeling the conduction, the heat flux, because you have, right, you've just put your finger on these two blocks and your surface temperature, your finger's the same. Well, the heat flux changes because the properties of the thermal conductivity are very different, where you have much higher thermal conductivity of the copper, so it's going to have more heat flux being pulled out. So it feels colder even though it can be at the same temperature. Okay. Any questions? And the second part of this, we're just looking at ratio of resistance of conduction and convection, which I don't think it's as important part of this problem. And then we have one more example, but I'm going to stop there actually. We'll do it at the beginning of the next class because we ended up ending a little bit sooner than the section of heat transfer I did earlier, and we stopped on this last problem. So we have one more problem to do at the beginning of next class, and we'll do start on chapter 2. Okay, so your homework, I'm going to move it to be due instead of tomorrow. I think it was due at midnight or 11:59. I'll move it to Wednesday, do it at 11:59, just so because we've got one more example problem to do. Okay, any questions? You guys don't ask as many questions as the first section, just so you know. But please let me know if you do have any questions, if you're working on your homework. The other thing to be very careful of on your homework, just like we've been doing with these problems, is to make sure you draw your schematic, and just like in those problems and this problem here, where you draw your schematic, label your heat transfers, and solve that. Okay, because if you're glancing at the solutions, they're going to do that step for you, and you're not going to get that first initial step, which can be the harder part, because after that it's plug in Newton's law of cooling, radiation equation. So all that part becomes the easier part of the problems once you've gotten that step. So if you're not getting that step of drawing your schematic, labeling your heat transfers, Whether it's on a problem that has a part A, B, C, D, it might be a different schematic. It might be a different boundary you got to draw. You need to do that part, okay? Because otherwise, if you see a problem you haven't done before, you're going to struggle with it if you're not doing that part of the problem, okay? So that's very important to work through the problem and understand that part of it, okay? All right. Questions? All right, so that's it for today, and I'll see you on Wednesday. Okay. All right. You guys have a good one.
Thank you, Professor. See you Wednesday.
Yep. See you
You
Wednesday.
too.
Yep. Bye.
Thank you.